Hello, guys. I'm going to go through some of the R code in Chapter 5 in the online textbook Econometrics with R. So we'll cover Chapter 5, which is hypothesis tests and confidence intervals in the simple linear regression model. So this chapter also does a little bit of simulation in R to try to get you to understand the basic idea that when we estimate a regression, we're estimating it for one particular sample. And if we took another sample, we would get different regression coefficients. And if we did another sample, we'd have another set of regression coefficients. And so we always want to think of our estimated coefficients as random variables, as being one outcome of a possible set of outcomes. And so sometimes it's useful when thinking about that to say, well, suppose I randomly generated a whole bunch of samples, calculated the regression coefficients for all of them, and then looked at the distribution. How many are big, how many are small, how many are towards the middle, looked at the distribution of those regression coefficients. So that's really easy in R. And so some of the scripts, some of the code in this chapter does that. I'm not going to cover those simulation ones. I think those are really interesting. And if you're at all want to try it, you just copy and paste and run it and try and figure it out. It's really useful to do that. I would encourage you to spend the 20 minutes it would take to cut and paste that and do that. I'm instead going to just focus on the commands that are doing what we need to do to calculate the hypothesis tests, the confidence intervals for a particular sample in a particular regression. So let's go over to the script, and I've already copied and pasted all of the commands over to a blank R script or an R script that I will share with you. So let's go over and look at that now. Okay, so here is the script, and as we see, we start out as usual with a clear environment screen. So I'm just going to again use Control Enter or Command Enter to use the keyboard to run the command. So I clear my environment window because I don't want to start out an R session with a whole bunch of objects over there in the environment. I want that to all be clear. And now I'm going to run my library commands. I've already run them, so my packages are already loaded. But in general, we have to do this every time we start an R session. And it's a good practice just to do it at the beginning of every script. So then we're going to load the California Schools dataset from the AER package, create two new variables, the student-teacher ratio and the test score. And so those are now created. And we can plot the data set with the student-teacher ratio on the x-axis and the test score on the y-axis, and have the fitted regression line there with slope negative 2.28 and intercept 6.98, as you see here. And notice the intercept here is not 6.98, and that's because the scale of the x-axis is not starting at 0, it's starting at 14. If it were extended to start at 0, you would see the line go through the vertical axis at 698. So that's our regression result. We can plot it. Now we can look at our regression results. So we use the LM command. We assign the regression results to reg1, and then we use Stargazer to display the regression results. Now, notice how the display works. And let me draw here. We have the coefficient negative 2.28 of our slope parameter and the coefficient 698 of our intercept. Below the coefficient, we have the standard error of the estimated coefficient. So the standard error of beta 1 hat. So that's always given just below. It's the usual default format is to give the standard error of the estimated coefficient just below the coefficient. And this 9.46 then is the standard error of beta 0 hat, the intercept, which we are rarely interested in economics. So those are the two standard errors. Remember, we calculate the standard error based on a formula. The formula is given to you in the Intro to Econometrics reading that I have for you. You should go and look at that formula. You don't have to memorize the formula. You can look online for the formula for the standard error. The default in R is the standard error under the assumption of homoscedasticity. We will, in this course, always be looking at the standard errors for heteroskedasticity, not here. This Econometrics with R does have that discussion in the chapter, and I encourage you to look at that discussion. But right now, we're using the default standard error, so that's the homoscedastic standard error. And we don't want to make too big a deal of the different standard errors under homoscedasticity and heteroskedasticity. The two turn out for many practical purposes to be very similar. They don't end up being that different. The data has to be quite exhibit a lot of heteroskedasticity for the standard errors to be different. So we'll look below at a little bit of some cases where there's a lot of heteroskedasticity, and there you would see a bigger difference in the standard errors. So let's continue on with our code. Notice that underneath we have our coefficient 2.28 and our standard error 0.48. So we can then calculate the T statistic, or sometimes we call it in shorthand the T stat. The T stat is just the coefficient beta 1 hat divided by the standard error of beta 1 hat. Now, normally we would have the we should add the null hypothesis of beta 1, so we'll sometimes call that B1 beta 1 0, the null hypothesis. In economics and by default in R, that's always 0. So that's why we often just say the T stat is equal to the estimated coefficient divided by the standard error, because the default null hypothesis is that the coefficient is equal to 0. That's the null hypothesis, the default null hypothesis. And so it's beta 1 hat minus 0. So that's just beta 1 hat. So we can calculate the T stat. And remember then the p-value of the t-stat, the probability of observing a t-stat of this size or worse for the null hypothesis that the coefficient is equal to 0. That is, we'll reject the null hypothesis that the coefficient is equal to 0 if we find an estimated coefficient that's so far away from our null hypothesis, taking into account our standard error of the coefficient, so that it's so far away that we would reject the null hypothesis. So that's what this notion of saying it's as far away as what we find, or even further, that's the probability that we're interested in. That p-value is given by 2 times the cumulative standard normal distribution of the negative of the absolute value of the t-stat. So complex formula, this is all in the readings. Encourage you to go back and look at that. I'm just doing it here on the board so that you see it once again, right? So we can calculate that, which we do right over here. So we'll calculate the p-value, and we see that it's 2.03 to e to the negative 6. So that's the decimal place, 6 zeros, 1, 2, 3, 4, 5, 6, and then 2, 2, 0, 3, 4. So this is a really, really tiny number. So the probability of getting this coefficient negative 2.28 is minuscule. If the true coefficient is 0, so the probability of finding the coefficient that we do, negative 2.28, or something even more negative, larger than in absolute value than 2.28, is so small that we should reject the null hypothesis that the coefficient is equal to 0. So we reject the null hypothesis that the coefficient is equal to 0. Notice that in the table, we have the 3 asterisks that tell us that the p-value, sort of a helpful guide, that the p-value is less than 0.01. In this case, again, the p-value is 0.00000, whatever, 6 zeros, and 2. And so it's very, very small, right? So that's our regression coefficient with our T statistic, our standard error, our p-value. Let's go ahead and look at that in slightly different form, in a variety of different forms. Let me clear the drawings here. So we can notice what we can do here. We can use the summary command and get just the coefficients with the standard error, with the T statistics, with the p-value. So that's another way of displaying results. Notice that if we add the square bracket 2, we'll get the coefficient. If we add square bracket 4, we get the standard error of the coefficient. So this is 2, this is 4. So I wonder what this is, 3, and this is 1. You can check out for yourself. And what would this be? 5. This might be 5. This might be 6. Let's see what 5 is. Indeed, that was 5, right? So we can recover the individual numbers. We don't have to retype them if we just know the syntax for recovering those numbers. So now we can calculate the t-stat. It's the coefficient divided by the standard error. So if I run that, notice that it now appears over in my environment. The t-stat is negative 4.75. Notice that that is indeed the t-stat here, right? I could have just said that call the t-stat be number 6, right, in the coefficients. And then I can calculate the p-value by hand. It's negative absolute value of the t-stat, so I get the same number that I got before. I can calculate the coefficient, beta 1, and the standard error of the coefficient, and then I can calculate the confidence interval. So the confidence interval now is the coefficient minus 1.96 times the standard error, or the coefficient plus 1.96 times the standard error. So that's my confidence interval for the estimated coefficient. I can also see that confidence interval in Stargazer. So if I add the command CI equals T, I get the confidence interval. And then there's another command in R, confidence interval, confint, that will give me the confidence interval for my estimated coefficient. So in R, there's always a variety of ways of doing the same thing, and it's up to you to use a variety of syntax and keep track of these scripts and save these scripts so that you can use them in future examples. You'd just be copying and pasting and maybe changing the variable names. Last thing I want to do today is, well, a couple more things. First is, let's suppose that the coefficient, the explanatory variable, were a dummy variable instead of a continuous variable. So suppose we scored the student-teacher ratio to be 0 if the class size was bigger than 20 and 1 if the class size is greater than 20. So we're going to make a logical variable here. I'm going to turn it into a numeric variable. So I'm going to add as.numeric here. So I'll run this. And now I have a 0, 1 variable. So I could write a table and CA schools $ small class dummy. And we see that 239 of the school districts have small classes, 181 have large classes. Now I can run reg2, where I have the dummy variable as my explanatory variable, and let's display the regression results. I get a coefficient of 7.168, which tells me that on average, small classes have test scores that are 7.17 points higher than large classes. So that's how I interpret a dummy variable. I say that on average, the dummy variable is telling me that on average, the small classes have scores of 7.17 higher than the large classes. So that's my interpretation of the dummy variable as a coefficient, the coefficient on the dummy variable. And finally, I can display both regressions in the same table. So notice I have regression 1 and regression 2. Each regression is a column. The student-teacher ratio, I interpret the coefficient as being, if the student-teacher ratio goes up by 1 student, test scores go down by 2. The small class dummy, if that's my explanatory variable, I interpret the coefficient as being that small classes have test scores that are 7 higher, right? So the two are, of course, compatible. If the student-teacher ratio is going up, you're not going to be a small class. You're going to be a larger class. So test scores going down. Small classes have higher test scores. Class sizes with more students per teacher have lower test scores. And I think, yes, we wanted to do a little bit of simulation here, and we can just run this code, right? So we're going to generate an X variable and a Y variable, and we're going to generate it so that the standard deviation of the Y variable depends on X. So its standard deviation depends on X, and then we'll plot it and add a regression line. So you see here the plotted data, this is a little simulation of data, and you see how the errors around the regression line get bigger as the X value gets bigger. So this is heteroskedasticity, not homoscedasticity. Notice if we made the errors not depend on the X value, we could do that simply by doing that. And now let's make the errors be bigger. So let's make them be something like this. Let's make them be even bigger. So you see how easy it is to play with R. There we go. Now we have homoscedastic errors, right? The errors are not changing depending on the level of the X variable. Let's go back to what we originally had. There's what we originally had and run that again, and we see how the errors change with the X variable. Now the last thing we have here is a example of heteroskedastic errors with real data. I'll let you run it and interpret it. It's pretty straightforward. And the last thing we have is some code here. I'm just going to run it all because all this code is doing is generating the graph up to here, I think. Sorry, up to here, right? Inside these lines. So we'll just run the whole thing. It generates that nice graph that shows you the normal distribution, the tails of the normal distribution with the 1.96, a possible T statistic of 4.75 that you might have calculated, and is useful for sort of understanding conceptually what's going on with the p-value in testing the hypothesis. So I hope this has been useful. I encourage you to read it and to ask me any questions that you might have.